In this example, we generalize the idea of time to failure somewhat, and instead of a rigid definition of time, we bring in number of cycles. So now we have a random number of cycles to failure. We did look at an example of some tests a few lectures ago. So it's looking at that in a more formal setting. So let's take a minute to read the problem, and let's solve it after that. So what we see here is the stress amplitude, that's a random variable. The coefficient k is a random variable, and the exponent m is a constant, a non-random number. In general, m is also a random variable in such situations, and it's correlated with k. But if we bring that in, it's going to just obscure a few things and make the computations unnecessarily demanding. So we are just going to treat m as a non-random constant for now. So this kind of gives an idea is the random time to failure. We are now talking about random number of cycles to failure. Random time to failure is parameterized by the stressor. So the stress amplitude here is the stressor, and that is now considered a random quantity. So this kind of gives an idea about what might be done in an accelerated test. This formulation really does not make it more physics-based. We are still treating the fatigue cycling and fatigue failure as a black box. We just have parameterized the problem with the random stress amplitude. So let's now look at the details. S and k are log normal random variables, so that kind of points that we need to take log and see what we get. So let's get on with the solution. S is log normal, so log S is normal with mean mu log S and variance sigma squared log S. And we know these formulas very well. We can derive sigma of log S and mu of log S in terms of the numerical values, and obtain the values as you see on the screen. We can do likewise for the coefficient k, and k is log normal, therefore log k is normal, and we have numerical values for sigma of log k and mu of log k. With these, we are able to find the properties of the random life, the number of cycles to failure n. So taking log on both sides, so log of n is a linear combination of log k and log s, m being a constant. So therefore, we have a linear combination of normals, which means log n is normal, which means n is log normal. So if it's log normal, so let's find the corresponding normal quantities, so mu of log n and sigma of log n. And just by using the definition which we have looked at before, the mean of log n and the variance of log n can be derived, and that's what you see on the screen. So the mean of log n is 13.9 and the variance of log n is 0.904, and that actually would give us the values, the mean of n and the coefficient of variation of n, and which happens to be about 112%, so very large coefficient variation, and a mean life of about 1.7 million cycles, and that n is a log normal random variable. So we are now in a position to solve part B, the probability that the component will survive 1 million cycles. So what we are looking for is that P of n greater than or equal to 1 million, and we can solve it, take the complement of that, make use of the fact that n is log normal, so log n is normal, bring in the normal distribution function, and the final answer is 0.55. So this would be a way of finding the fatigue reliability.